Hey, hello. So question 17, an elastic cord was fixed between the end of an air track and a glider. The glider was pulled to the right, given the elastic cord extension as shown. Obviously, when you extend any wire, there's elastic energy stored onto your wire. The glider was released and it moved to the left. Why did it move? Because elastic energy was it was transferred to kinetic energy. A light gauge was used to measure the maximum velocity. This was repeated for different values of the extension. He obtained the following results. And this is what they plotted. They plotted velocity against extension. And I know that the gradient of this graph is velocity over extension. And it's always important to consider what the gradient of the graphs they give you represent, just because most of the time you end up having to use this gradient somewhere later on the question. So gradient is just velocity over extension. And the principle of conservation of energy, which is energy cannot be created or destroyed, it could only be transferred. So any question that talks about this principle is basically saying use energy transfers. So from kinetic to gravity, or in this case, elastic to kinetic. And what this principle predicts is it should be a straight line. Well, a straight line would mean that your independent variable is proportional to your dependent variable. Or in this case, in this context, your velocity is proportional to your extension. So the conservation of energy predicts that this should be the case through the origin. For the range of values of the extension used, the elastic cord obeys Hooke's law. What does it mean if something obeys Hooke's law? Well, it means that it obeys the following equation. Force is equal to the spring constant multiplied by the extension. Explain this prediction, i.e. explain how the conservation of energy leads to this relationship, which is velocity is proportional to extension. Well, let's start by considering the energy transfers. Well, it's from elastic, so half, force multiplied by extension, and that's all converted to half mv squared, assuming obviously no energy is lost. No work is done against frictional forces, so it equals kinetic energy, which is half mv squared. The halves cancel out, so you get force extension is equal to mass times velocity squared. This is a slightly useless equation. In fact, it shows the opposite, because just by looking at this, you could see that velocity squared is proportional to extension. You don't want any squared. You just want velocity is proportional to extension. So we're going to have to consider what else can we do. Well, I know mass is constant. Mass never changes, so I'm not going to bother fiddling with that. But I do know the force, of course, does change. The more you extend it, the larger the force you apply, the more it extends it. So let's swap force with Hooke's law, because we know it obeys Hooke's law. So let's swap force with K times extension. So K times extension times Y extension is equal to mv squared. So K extension squared is equal to mv squared. We could rearrange and say that velocity squared is equal to K over m. So I took this m to the other side. I divided both sides by m. So K over m extension squared. We don't want velocity squared is proportional to extension squared. We just want velocity is proportional to extension. So let's just square root both sides. So this becomes v is equal to square root K over m, and then also square root extension squared, which is just extension. And we know that the spring constant and mass are both constants, i.e. they don't change. The mass is the same throughout the experiment, and it's the same string, so it has the same stiffness. So this is a constant, so we could deduce from this that the velocity is proportional to the extension. So yeah, we've used the conservation of energy to prove that it should be a straight line, i.e. the velocity is proportional to extension. Every time it says straight line on a graph, it just means the two variables plotted are proportional to each other. Okay, determine the stiffness K of the cord. So we need K is equal to something, and I'm going to use this equation I had in the previous part. You could, it could be tempting to just say K is equal to F over X. The problem with that is you don't know any values for the force. The graph doesn't give you the force, it gives you velocity instead. So I'm not going to use this equation. And usually you should realize that part II involves information from part I. This is like the case 99% of the time. So I'm going to use perhaps this expression here. You could have used any of the expressions above, but this one's the easiest. So I'm going to say that K multiplied by extension squared is equal to mv squared. And I'm going to make K the subject. So K is equal to mv squared over extension squared. And it's like, what is the velocity? What's the extension? Well, let's go back to the graph. We could work out velocity over extension, which is the gradient. That's why it's always important at the start of the question to just write down expression of what the gradient represents. So this is equal to mass multiplied by the gradient squared. Why? Because the gradient is equal to velocity over extension. So velocity squared over extension squared is gradient squared. Right, so this squared is equal to this squared. So we know the mass is 0.3 kilograms because it's given it in grams, and the gradient, we're going to have to work it out. Let's say, like, I'm going to draw my triangle from this point. So it goes from 0.2 to 0.3. So I'm going to say that my the length of x, or the base of the triangle, is 0.3. It's in meters already, so I have to convert. And this is in meters per second, so I have to convert. And this goes from, I don't know, let's say 4.4 to, this is around 1.8. So 4.4 minus 1.8 is 2.4, 2.6. So 2.6, meaning the gradient is 2.6 over 0.3. So let's put that in our working out. So where equals, was it 2.6 over 0.3? I actually have the memory of a fish. Yes, it was. So we're going to do multiplied by 2.6 over 0.3. That's the gradient, but you want the gradient squared. So let me put that in my calculator quickly. 2.6 over 0.3. I got 22.5. And the unit is, well, if you ever want to remember what the unit is, use the equation to help you. I know spring constant is force over mass. So I could write newtons per meter. So 22. Am I going to use 3 significant figures? I guess I will. Why not? I guess it's probably better to use 2 significant figures because the values in the graph, like this 1.8 and this 2.6, are to 2 significant figures. So actually, I'm going to write 23 is equal to 23 newtons per meter. When the glider was moved to the right by more than 0.5 meters, the graph began to curve. So if you look at the graph, it's basically saying once you stretch it beyond 0.5 meters, it begins to curve. And you should know the reason this is the case is because it no longer obeys Hooke's law. So before it was obeying Hooke's law, now it won't. So we're going to phrase this like so. After stretching, or sorry, extending is probably a better word. After extending it by 0.5 meters, the cord or the string or whatever it is no longer obeys Hooke's law. Obeys Hooke's law. Why is that the case? Because it has stretched beyond the elastic limit or limit of proportionality, because it has been stretched beyond the limit of proportionality. Good. And we know Hooke's law is the force is proportional to extension up to the limit of proportionality. And this is after the limit because it began to go. And then we could say by extension, therefore, force is no longer proportional to extension. And that would mean that the velocity is no longer proportional to extension. So, and hence velocity is no longer proportional to the extension. Good, because we figured out here that velocity is proportional to extension, and we know extension is proportional to force. So if force is no longer proportional to extension, that would also mean force is no longer proportional to velocity. Okay, question 18. A student carried out an experiment to determine the Young's modulus of copper. She added a mass m to the free end of a sample of copper in the form of a long, thin wire, and the corresponding extension was measured. This was repeated for increase in masses. State the meaning of the term Young's modulus. That's just stress over strain. So Young's modulus is the stress divided by strain of a material. Something like that, or the ratio of stress over strain. The student repeated the measurement of the diameter of the wire at different positions. And you should remember from the required practical, the reason you do this is because it makes your answer more reliable. Because maybe one part of the wire is slightly thicker than the other part of the wire. So you just want to use your micrometer. How do you draw micrometer? I don't know, something like this. You want to use your micrometer at different positions. And also, sometimes you might end up squeezing the wire a bit too much. So you're compressing the wire, meaning you want to get a smaller diameter than the actual diameter of the wire. So it makes sense to measure at different positions and then work out an average, which is what she did. I determined the cross-sectional area. We know that area is equal to, because it's a wire, so it's a cylinder. The cross-section of a circle, the cross-section of the cylinder is a circle. So pi r squared or pi d squared over 4, which is what I'm going to use. So I need a diameter and I need the average diameter. So I'm going to add all these numbers up and divide by 4 and then divide by 1,000 because it's giving it to me in millimeters. So do this plus this plus this plus this, divide by 4. 0.23 plus 0.235 plus 0.23 plus 0.24 divided by 4, and then divide by 1,000 to go from millimeters to meters, and I get the following. So this is equal to pi multiplied by the diameter squared, which is 2.3375 times 10 to the minus 4 squared over 4, and what you should get is, I got 4.29. I'm going to put it up to 3 significant figures just because these were all 3 significant figures as well. So 4.29 times 10 to the minus 8, although it's actually fine in this scenario to use 2 significant figures because you did work out an average. So what's the unit? Well, it's area, so it's meters squared. The student plotted a graph of m against x. She measured the gradient and obtained the value of 195. For the gradient is going to be m over x because she plotted a graph of m over x, right? So that's what the gradient is going to represent, and that's equal to 195. Determine the Young modulus of the copper. Well, Young's modulus is stress over strain. Stress is force over area. Strain is extension over the length. So what you could do is multiply the ones further apart and the ones closer apart to get into one fraction, which is force multiplied by the length over the area multiplied by the extension. Well, we don't know what the force is. It would be nice to know what it is. Well, in this case, it's the force of gravity acting on the mass, which is weight. And I know that the force is the weight, and weight is equal to mg, right? So I'm going to swap this with mg. So this is mgl over area multiplied by the extension. What I can see is in this fraction, because we don't know what the mass is, and we don't know where the extension is. We do know what the length is, we do know what the area is, and we do know what g is, just 9.81, but we don't know what this mass is, and we don't know what the extension is. However, we do know that mass over the extension, which is the gradient, is 195. So what I'm going to do is I'm going to rewrite this equation as mass over extension, then g multiplied by g times L multiplied by the area. So this is the same as So as you can see, this mass over extension is the gradient. So this is the same as 195 multiplied by GL over A, which is 195 multiplied by, just check out, I have to convert any units. Okay, no, 9.81 multiplied by the length, which is 3.5, multiplied by the area, which we worked out in the previous question. Try use the unrounded value, but I lost that value. So I'm just going to write 4.29 times 10 minus 8. Give me 10 seconds. Put this in my calculator. And I get 1.56 times 10 to the 11. And the unit for Young's modulus is the Pascal, right? Because the unit of stress is pascals or newtons per meter squared. And the unit of strain, it does have a unit. So you're just doing pascals divided by no unit, which is just pascals, or newtons per meter squared. The experiment was repeated by another student using a 2-meter length of the wire, or of the copper wire. Suggest how the values obtained for the gradient and the Young's modulus will differ between the students. Well, I know the gradient is mass over extension. And I know that if he has a shorter wire, so this is the gradient. He has a shorter wire, meaning it's going to extend by a smaller amount, because you should know that the length of the wire is proportional to its extension. So if it's extending by a smaller amount, you're dividing by a smaller number, so your gradient is going to be larger. So let's start by commenting on the gradient. So there will be a larger gradient. And then finally, what's going to happen to the Young's modulus? Well, Young's modulus is a property of a material. It doesn't change. It's not like stiffness, where you could have this, two objects with the same material, but they'll have different stiffnesses because they either have a different length or a different cross-section or a different blah, blah, blah. Young's modulus is different. Just like strain, it doesn't depend on the dimensions of your material. It only depends on the material. And because he's still using copper, which is what he used before, that means the Young's modulus will not be impacted. The Young's modulus will remain the same as he is using the same material. Honestly, it's a bit of a trick question. It said and hence. So you'd expect, oh, this increase, therefore something happened to the Young's modulus. But no, nothing will happen to the Young's modulus if it's the same material. If you look at the equation for Young's modulus, this one here, yes, the gradient, which is m over extension, has increased. However, G times L over A has decreased. Why? Because the length has decreased. And these two effects kind of cancel each other out. Okay, have a lovely evening.